Okay, so hello everyone. This is lecture 2 of Arithmetic and Statistics. So last time we did very classical 1800s analytic arithmetic and statistics. We're going to try to move to more algebraic arithmetic and statistics, but still 1800s. So we'll get to more modern stuff soon. Then we'll jump quite a bit in time. Okay, so one of the themes that we talked about that I mentioned briefly last time was that in arithmetic and statistics, sometimes you want to count number theoretic objects relative to one another. You know that there are infinitely many of each kind, but now you want to compare how abundant one over the other is. So here's one classical example, famous example, which is the following: that every odd prime is 1 mod 4 or 3 mod 4. So one would like to know, is there the same number of such primes up to x? Now, Johann Peter Gustav Lejeune Dirichlet, he proved that there are infinitely many such primes. So he proved what we now call Dirichlet's theorem on primes in arithmetic progressions. He proved that if a and n are relatively prime numbers, then there are infinitely many primes that are congruent to a mod n. Okay? And then de la Vallée-Poisson, he proved that there is an asymptotic behavior for that. Just like the prime counting function, you can count how many primes of in each congruence class are there. And remember that we discussed last time why that would be there. It's just counting the integral is what we found out to be asymptotic to the prime counting function. And then you're dividing by 1 over phi of n, because 1 in phi of n classes of prime numbers is the one you want, the one that is a mod n. So there are that many. Okay? So if you run the heuristic argument that we were running last time, you would come up with this as your explanation of how many there should be, and then somebody went out and proved it. Okay? All right, so there is again. So how about when we're talking about numbers modulo 4, except for then prime 2, then there are primes that are 1 mod 3 or 4 or 3, 1 mod 4 or 3 mod 4. And according to Dirichlet, they both are supposed to be asymptotic to the same function. So this seems to be indicating again that we should expect to have the same number of primes. So go out there and start looking for primes of each kind. And it turns out that as you start looking for those, the primes that are in red, those are the 3 mod 4s, and in blue are 1 mod 4s. If you start counting, you start with a 3 mod 4, then a 1 mod 4, then 2 3 mod 4s, and then there's start to be a race. And it turns out that the red ones are always ahead or equal. Okay? So it turns out that it seems like the 3 mod 4s are a little more abundant than the 1 mod 4s. It's subtle, but it's sort of there. So if you start counting, this is something that Chebyshev realized and talked about in 1853. There seems to be a bias towards the numbers that are 3 mod 4. And then you can count and then see that up to 100 there are 13 versus 11. Up to 200 there are 24 versus 21, and so on. And they're just a little bit more abundant. They're asymptotically the same numbers, but there's something else going on. There is some sort of like second term counting function that so something is going on. So I took this table. There is an article by Granville and Martin, prime number races, that is fantastic, and I highly recommend it. There is a link in the website, by the way, in the website for CTNT. There is, under my header for my lecture, there is a link to notes and resources. And there I have all sorts of links to all sorts of different papers of different flavors. And this is one of them. Okay. Some other, by the way, an aside is that there is very recently Robert Lemke Oliver, who will be coming to the conference, and Kanan Soundarajan, they published some other unexpected bias in the distribution of primes, this time consecutive primes. I will not try to describe here what they did, but this is somewhat in a sort of like a similar flavor of like what happens with these 1 mod 4s and 3 mod 4s. So it's something like very interesting that has discovered just very recently. Okay, going back to the 1 versus 3 mod 4. So there is actually equality a bunch of times. They tie up, but it seems like the 3 mod 4s are always ahead. There is equality at 5. You see the 3, then 5. So there's been the same number of primes. But after that, it just seems like that the 3 mod 4s are always winning or tied. So that is actually not true all the way. The first inequality flipping, so when the 1 mod 4s go 1 ahead, is at 26,833, and then the next prime they tie, and then the 3 mod 4s get ahead again. So it does flip. And in fact, Littlewood showed that there are infinitely many values of x where there is a flipping, where the 1 mod 4s are a little bit ahead. But yet, there is just a very few. It seems like they get ahead and then they go, they start losing again right away. And Nepowski and Turan, they actually conjecture that 100% of all integers are such. So asymptotically, everywhere, the 3 mod 4s are winning. Well, it turns out that they were wrong. That is not true. Rubinstein and Sarnak, they showed that the limit of that asymptotic, okay, if you try to do the statistic of how many numbers are sort of like satisfying Chebyshev's bias, then you would look at this function and try to see where that goes as x goes to infinity, and it turns out it does not have a limit. So that cannot be true that 100% of them are satisfying the inequality. But yet, some other theme of arithmetic statistics that we talked about is that maybe we're not counting the right way. And I will not go into detail either, but what one incredible insight of Rubinstein and Sarnak is to say that we are not counting these numbers in the right way. We should be using a logarithmic measure. And when you use a logarithmic measure, then instead of counting how many numbers are there with that property, so this s of x right here, this is in yellow now is s of x, so here and here again, instead of counting 1 for every time one of those happens, you have to count 1 over x for each one of those and then divide by 1 log x. That's something that's called a logarithmic measure instead of like the regular measure of the integers. And under that measure, you can count how many exceptions are there. And what they show is that essentially 99% of the times, Chebyshev was right.
I think they had to assume like GRH or something.
Yes, I think that you are correct, that this actually assumes GRH, which... but they can do that for the 1 versus 3 mod 4, and they do it also for 1 versus 2 mod 3. It turns out that there's sort of like a similar bias in several of these races, and they can compute what's the percentage of times that one team will be winning versus another. It's just very, very interesting that by changing the way you count, then you can actually get different results and sometimes prove one thing versus in another type of counting there is no such proof. Okay, so why are the primes that are 3 mod 4 slightly more abundant than the primes that are 1 mod 4? I will not go into it again, but in the paper by Granville and Martin, the prime number races, they do a little bit of an explanation in there what's happening. There is something that's happening with the squares. That is the issue here. So the fact that 1 is a square mod 4 while 3 mod 4 is not a square, that's sort of at the heart of the difference in the counting of why they appear more often. And we know that somebody proved already in one of our lectures that the numbers are 1 mod 4. There is some splitting happening in a number field versus the numbers that are 3 mod 4. We know that there is some difference, some significant difference between the numbers that are 1 mod 4 and 3 mod 4. For instance, it was already known by Fermat that an odd prime P is a sum of 2 squares if and only if P is 1 mod 4, right? So that is one difference that is related to 1 mod 4 being a square versus 3 mod 4 not being a square. And so that is also equivalent So that what that's saying is that there is a quadratic form, x squared plus y squared, that represents p. And that's as much of a segue as I'm going to give you into the next topic, where we're going to look at what numbers are represented by quadratic forms and which ones are not. Okay, so this is another classical example of a topic that saw a lot of interest by Gauss and then followers of Gauss. And Gauss himself had a lot of pages of his Disquisitiones dedicated to quadratic forms. So let's see what we are trying to do here. So as I said, this is my more algebraic form of arithmetic statistics. So as I was just saying, a prime is of the form 1 mod 4 if and only if there is two integers whose sum of the squares is p. And that is an example. X squared plus y squared is an example of a binary quadratic form. And we would like to know, well, okay, what if I change the quadratic form, choose another one, what primes are represented then? Maybe there is some other explanation for counting of primes in one way or another. Some other quadratic form might appear and have something to do with it. So, for instance, here's another quadratic form, a squared plus 2ab plus 2b squared. How about, are there primes of that form, and which primes are of that form? Well, for that form in particular, it's actually pretty simple, because if you change variables x equals a plus b and y equals b, then the form x squared plus y squared becomes a squared plus 2ab plus 2b squared, and that change of variables is invertible, and the inverse change of variables also have integer coefficients. So whatever integers you had for x and y will be integers for a and b, and whatever integers you find for a and b representing a prime will become integers x and y. So there is an if and only if that both forms represent exactly the same primes. Okay, so what we would like to know is now, instead of, I would be able to count quadratic forms by the size of the coefficients, but actually I'm interested now in classifying quadratic forms in families that have some arithmetic property. And I just want to, this now set of all the quadratic forms, I want to organize them in one way or another that tell me some arithmetic property. So for instance, I want to find arithmetic or algebraic ways to find my way into a subfamily of all those quadratic forms that represent exactly the same primes, for instance. Okay, so we've sort of done a little example of that. If you take the quadratic form x squared plus y squared, we've changed variables, a simple change of variables that you can represent in matrix form, and then you see that that change of variables did what I said. It goes from integer coefficients to integer coefficients because the matrix is in SL2Z. It's a matrix of determinant 1, so the inverse has integer coefficients, and it also has determinant 1. So if I replace that matrix by any other matrix in SL2Z, I will have another change of variables that will bring me to another quadratic form that will represent the same primes. Okay? So then what that means is that there is an action of SL2Z on binary quadratic forms given as follows. Matrix M in SL2Z, I can multiply it by little f, by my quadratic form. How? To get a new quadratic form where now the inside is just going to be m times xy. Okay, that's what's happening up above. I've changed the quadratic form x squared plus y squared. I've changed variables into a, b using such a matrix.
Is that associative?
Is that associative? Well, no, because of the matrix multiplication. I don't think so.
Okay.
Yeah, because, for now, I'm just going from one matrix, from one binary quadratic form to another. just using those matrices to go from one place to the other. And now what I'm going to do is just find all the families that are related by one such change of variables. Okay? So, by the way, there's an alternative way to interpret a binary quadratic form, which is by representing it in this form. So use a triple product of a vector, a matrix, and a vector. And if you write it in that form, then in general, a quadratic form is given by a matrix of that form. And when you multiply, when you act on your binary quadratic form by the matrix, then what you're doing is that matrix that is associated to your quadratic form is changed by, you multiply on the left and the right by m and the transpose of m. Okay? So that way it gives you, you can talk about binary quadratic forms just in terms of these symmetric matrices. Yes? One question.
Why can't we look at orbits under GL2Z? Why are we looking at S? Why are we S?
So what I want is to preserve what integer values they represent. If you use a GL2Z, then what's going to happen is that the inverse matrix, which is going to be the inverse change of variables, will not have integer coefficients. So there might be cases where this form represents with integers, but when I try to now, okay, I'm going to bring that representation back to this other form, the x and y values, that a and b were integers, the x and y values now will be rational numbers.
Doesn't GL2Z just mean that the determinant is plus or minus 1?
Oh, I'm sorry. I thought you were saying GL2Q. So yes, in GL2Z, so now with minus 1, I can also do that, but if I change by a matrix that has determinant minus 1, then I can do SL2Z and a determinant minus 1. So say, so you can also switch with minus 1. I was going to say, for some reason I was thinking of minus identity, but that's as determinant 1. Yes, you can also change with GL2Z. You're right. Yeah. So we can do changes of variables like that. So I think that's right. We can write it here. That we can extend that and do a little bit better because we can do determinants being plus or minus 1, and that is fine too. Okay, so we can represent our matrices in this way, and you can change variables by doing that and act on your matrices. And so, for instance, if what we've done before was to start with the quadratic form x squared plus y squared, I chose my matrix in SL2Z 1, 1, 0, 1, and then I acted on the left and the right and got a new matrix, which is 1, 1, 1, 2, and that one corresponds now to the new form that I got to. Yes? If you act by minus identity, then because it's a quadratic form, you'll get exactly the same form. But if you change by minus 1, 1, then it is a little bit different. It changes the cross term, the xy will change it by minus.
Do you want to take away that minus identity?
I'm not saying that action is faithful.
Okay.
I want the whole family, so I'm just going to consider a set that I'm going to start with one form and act all the time, every action I can do to get to all the other forms that represent the same numbers. So I'm not looking for something like best possible and do it faithfully and so on. I'm just finding a big family of forms that represent the same numbers. So the matrix, so we went from one form to the other using that change of variables, and we are interested in, I guess, we will do GL, I think, change by by GL, and the set of all orbits. I got like out of whack. Hold on. All right, let's try that. Okay, so and then we're interested in seeing like, well, what are the set of all orbits that you get when you act in this way? So in particular, when there are two binary quadratic forms in the same class, that's going to be our families of binary quadratic forms, where I want to organize my binary quadratic forms by, are they equivalent under SL2C? Because if so, they represent, for instance, they represent the same primes. Okay. So, for instance, if you have two forms, 11x squared plus 5xy plus y squared, and x squared plus xy plus 5y squared, are those equivalent? Okay, so if we want to find are these equivalent, when you have two objects that you want to check whether they're equivalent under some equivalence class, then you want to look at invariants for those equivalence classes. So here is one such invariant. Since we are I'm representing forms by a matrix, and when I change it by another matrix, I get some product of matrices. If this M is of determinant plus or minus 1, the transpose will have determinant plus or minus 1, and then both will have the same determinant. Okay, so one such invariant is the determinant. So the determinant of one matrix in a class will stay invariant in the whole class. So that's one way to tell whether they are in the same class. So we define that invariant. That's what's called the discriminant of the form. So if you have a form ax squared plus bxy plus cy squared, the discriminant is b squared minus 4ac, as you would probably imagine. And if you take the form that we talked about before, that discriminant is minus 4. And if you have a non-zero d, then the discriminant of x squared minus dy squared is 4d. And if you have, for instance, x squared plus xy plus y squared, that corresponds to the matrix 1, 1 half, 1 half, 1, and the discriminant will be minus 3. Okay? So we would like to, we can actually define the same discriminant for any element of the class. Since the discriminant doesn't change, you take a class of binary quadratic forms, you pick one representative and compute the discriminant of that one. That will be the discriminant of the class. And what we know is that if two binary quadratic forms are in the same class, they have the same discriminant. But is the converse true? If they have the same discriminant, will they actually be in the same class, or are there forms with the same discriminant that are not in the same class? So, for instance, are these two forms equivalent? Well, they do have the same discriminant, so are they actually equivalent? They are both forms of discriminant minus 19. So are they actually equivalent? All right, so now we need something better to actually tell whether two forms are equivalent, and that's something that Gauss did in the disquisiciones, and he found that we're going to limit ourselves for now to discriminant, to negative discriminant, that every equivalence class of binary quadratic forms contains a unique reduced representative with the property, with such property that B is between minus A and less or equal to A, and A is less or equal to C. And if A is equal to C, then B is positive. So there is one such equivalence class in each, there's one such reduced form in each equivalence class. And so, for instance, according to that, the first form, x squared xy plus 5y squared, is reduced, but not the second one, because A is bigger than C, and that's not allowed. 11 is bigger than 1. So Gauss, of course, he also came up with a so this is something went wrong with my slide here. What happened? Gauss. to find the reduced representative. So Gauss came up with an algorithm to find these, so he proved that there is a reduced representative, a unique reduced representative, and he gave an algorithm. So here are the steps in the algorithm. So if C is less than A, then you flip X and Y essentially and change signs. If B is bigger than A or B is less or equal to minus A, then you change by one translation like that, where the little k is given as follows. B prime is going to be a number that is congruent to 2A, is going to be basically the least residue that is between minus A and A of B modulo 2A, and then you take k such that B prime is equal to B minus 2KA. We will do an example of that in a moment. And if C is equal to A, but minus A is less than B, then you flip again and switch variables. Okay, so for instance, if you want to reduce that one that we saw, that form that was not reduced, then because 11 is bigger than 1, you change variables with 0, minus 1, 1, 0. And to change variables, you follow the formula we had before, and that leads to a form x squared minus 5xy plus 11y squared. And that one is not reduced yet. So minus 5 is less or equal to minus a, so that's no good. And then you find b, what is the congruence class modulo 2a? That's 1, so minus 5 is congruent to 1. So I'm going to pick b prime to be 1 because it's between minus 1 and 1. And then find my k to be minus 3, so that b prime equals b minus 2ka. Okay, so there you go. So you pick k to be minus 3. Now you change variables with 1, 3, 0, 1. And with that change of variables, it brings you to a quadratic form that is reduced now. And it's actually the first one I was trying to compare with. So they are actually equivalent. The one I started with and this one, they're both two forms that are equivalent. Okay? All right, so the two forms, x squared plus 5y squared and 2x squared plus 2xy plus 3y squared are actually both reduced, both of discriminant minus 20, but these ones are actually not equivalent. So as before, we were comparing two and we found they were equivalent. These two forms of discriminant minus 20 are not equivalent. They're both reduced, and we know that there is a unique reduced form. So these are two different ones. Okay, so here is a question now. Fix a negative discriminant D and let BQF D be the set of all binary quadratic forms of discriminant D. How many classes are there in the quotient? So that question, that was also of great interest to Gauss, and he answered it for negative D. You can answer that quite easily using what we just learned. So because there is, for D less than 0, there is these reduced forms, you can prove the finiteness of this class group in an easy way. So remember that we can always find one of those reduced forms, and therefore the absolute value of D is negative, so the absolute value of D is minus D. That's 4AC minus B squared is going to be bigger than 4AA minus A squared, so that's 3A squared. That tells you that A is less or equal to the square root of D over 3, and that limits the options for A. So that gives you only finitely many options for the value of A, and B is sandwiched between, the absolute value of B is between, B is sandwiched between minus A and A, so the absolute value of B is less or equal to A. There are finitely many options for B, and C is actually determined by A and B. So there is actually only finitely many possibilities for reduced forms when the discriminant is negative, and you can list them all. And you can list them all, and then just check when you know how many are there that are reduced of that discriminant, and figure out how many classes are there. So there, in particular, there are finitely many classes when D is negative. So the number of classes is actually denoted by h of d. It's called a class number for the binary quadratic forms of discriminant d. And notice that d itself, the discriminant, is b squared minus 4ac is a number that is congruent to 0 or 1 mod 4. And when d is 0 mod 4, there is a form that is reduced. And when d is 1 mod 4, there is a form that is reduced with that discriminant. So there is always at least one such quadratic form with that discriminant. If you give me a fundamental discriminant, so a number that is 0 or 1, then there are forms with that discriminant. There is at least one. The question is now, if you give me one, how many classes will there be? So in particular, h of d, the class number, is bigger or equal to 1. And when you are looking at forms of discriminant minus 4, like the one we started with, there is exactly one reduced form. That's the one. When you're looking at class number 2, or discriminant minus 20, it turns out there are 2 of them. So all the binary quadratic forms of discriminant minus 20 are either equivalent to x squared plus 5y squared or 2x squared plus 2xy plus 3y squared. And I've left it as an exercise to actually show these class number equalities. Okay, so back to representing primes by quadratic forms. So something I'm not going to prove is the following, that if you have a triple that is relatively prime numbers a, b, and c, and p as a prime, put d to be b squared minus 4ac, then the form with those coefficients a, b, and c represents the prime p. If it represents the prime p, then d is a square modulo for p. And sort of conversely, if d is a square mod for p, then there is a binary quadratic form of discriminant d that represents p. Not that one in part 1. It just says that if you can represent p, d is a square mod for p. If d is a square mod for p, then there is a binary quadratic form of discriminant d that represents p. Okay? So what happens? By the way, for 2, it's not very mysterious. You can find the form if you play a little bit what form would represent it. But for instance, when you have only one class of quadratic forms in your discriminant, then there will be sort of like an infinitely if in this proposition, namely that, okay, if you have a form that represents p, then d is a square mod for p. But if d is a square mod for p, then there is a binary quadratic form that represents it, but they are all equivalent, so all of them represent it. So any form of discriminant d will represent p as long as d is a square mod for p, if the class number is 1. Okay? So what that means, for instance, when you have a binary quadratic form of discriminant minus 4, is that it represents p if and only if minus 4 is a square mod p, so for odd primes. So if minus 4 is a square, so if minus 1 is a square mod p, which only happens when p is 1 mod 4. So we got back the condition that we knew from Fermat. Okay? But now we have other places where this happens, that there is only one class, one element, or that there's only one class in this discriminants. So when does that happen? When can we apply the corollary that the class number is 1? So with work of Higner, Baker, and Stark, all put together, they completed the class number 1 problem of Gauss. He wanted to find out all the discriminants where the class number is exactly 1. He wanted to classify, okay, when is it exactly 2? When is it exactly 3? He proved that or he conjectured, I think, that the class number would grow, so he knew there would be like some finite lists. So here is the full lists. So only when d is minus 3, minus 4, minus 7, minus 8, minus 11, minus 19, minus 43, minus 67, minus 163, the class number is exactly 1. But for those cases, we have our corollary that if h of d is 1, then so there will be a discriminant D quadratic form that represents P if and only if D is a square mod for P. Okay? So, for instance, if you take the form x squared plus xy plus y squared, that will be equal to P, to a prime P, if and only if minus 3 is a square modulo P. When you take D equals minus 8, the primitive form is x squared plus 2y squared. So those represent P if and only if minus 2 is a square mod P. However, when you reach, if you go up to a class where there is no class number 1, now it's not the corollary doesn't work. It's not an if and only if. It says that if D is a square mod for P, then there is a form that represents, but now there is 2 forms. So each one of the forms represents a different set of primes. So with minus 20, now there is 2 representatives for classes, 2 distinct representatives. There's 2 classes. Here are the representatives. And the first one represents primes that are 5 or 1 or 9 mod 20, while the second one represents the prime that is the number 2 or 3 or 7 mod 20. Okay? So now there's a split that one form represents some of the primes, the other form represents some of the other primes. Okay. So now, so we were looking at what primes are represented by quadratic forms, but what numbers are represented by binary quadratic forms. That's another classic example, ones that you prove that a prime is represented as a sum of the squares. If the prime is 1 mod 4, now you want to prove, okay, what numbers are a sum of 2 squares, right? To prove that, you use this famous equality that a product of sums of 2 squares is itself a sum of 2 squares. This was interpreted by Gauss as a property of binary quadratic forms, where you have a one binary quadratic form, you multiplied it by another binary quadratic form, and you got a new binary quadratic form. And not just any 3, you started with a quadratic form of discriminant, in this case minus 4, times minus 4, you got a discriminant minus 4 quadratic form. More generally, you can do the discriminant, so what that would be minus 4d, I think. So if you multiply this one by that one, you also get that quadratic form. So he asked himself, okay, so what if I have just any 2 quadratic forms of discriminant D? Can I do the same thing to study like what numbers are represented by binary quadratic forms in general? And he figured out that that actually happens. That if there is if you have 2 just quadratic forms of discriminant D, F and G, you multiply them together, there is a way to write that itself as a new quadratic form of discriminant D, okay? And where the M and N are just some bilinear forms in the coefficients, in the variables x, y, x prime, y prime. Just sort of like this. So this would be an example of, the bilinear forms M and N that are below. So here is another example of what Gauss called composition of quadratic forms. So the composition of these 2 quadratic forms, those are 2 quadratic forms of discriminant minus 71. And then he figured out that if you multiply them together, then you get this other quadratic form. What is the discriminant of that one? Will be b squared, so 1 minus 4ac, so 4 times 2, 8 times 9, 72. That's minus 71. That's also discriminant minus 71. And there is that equality with these crazy coefficients for the bilinear forms that go as M and N. Okay? So there is this way to go from one quadratic form and another quadratic form, multiply them. So there is the making of a group law inside the classes of binary quadratic forms. Now, this Gauss composition law was extraordinarily complicated, and many people try to read through the pages of like how Gauss explains how to find those bilinear forms, and it's just very difficult to get through. It's a lot of like algebra, but I just wanted to show you, this is actually Gauss. So in article 234, he starts talking about the composition formarum, and the whole thing is called compositio formarum. That's the form composition. And then you can see he starts explaining how to build those bilinear forms that will relate one quadratic form with another. And you can see the algebra that he starts to go through, explaining how you're going to find those new variables, x and y, out of the old coefficients. And then he explains like how to go through some like cases. It's crazy. It's just nothing that seems of any intuition whatsoever. So his students tried to make head and tails out of this, so make sense out of this. And Dirichlet, who was one of Gauss's students, legend says, I've read it a couple times, that he traveled everywhere with a copy of his advisor's book, the Disquisitiones, that he slept with it under his pillow, apparently for like 3 years or something, hoping that inspiration would come at night. Whatever he did with the book, it actually worked. He explained composition in a couple of different ways that are simpler to understand how composition worked. But most importantly, he started to rephrase that in terms of ideals. So Dirichlet's work morphed into Dedekind's work, where he actually set it up as algebraic number fields, ideals, and now we're going to see how these ideas of Gauss, actually the binary quadratic forms, are related to ideals in quadratic fields, and how the composition is actually the group law that happens in the ideal class group. And from the ideal class group, it's a lot easier to understand what's happening. You take an ideal I, an ideal J, look at their classes, multiply, this will be another class, and this other class will somehow be associated to another quadratic form, and this is what's happening with Gauss. Okay? So let me show you how this actually happens. So we're going to move to number fields. For instance, q adjoint the square root of -5. So here is Dedekind looking very sharp. We're going to concentrate for now in quadratic number fields. In fact, in imaginary quadratic number fields. So here's a quadratic imaginary, or for now, just a quadratic field of a square root of d. Then you know what the ring of integers will be depending on the class of 2 of d modulo 4. And what I'm interested in is looking at all these rings put together. There is a height for that in terms of the discriminant of the number field. And I would like to know how many of them are PIDs as I go along if I order them by discriminant. We're going to restrict ourselves for simplicity to the negative discriminant ones. So now I'm going to order by absolute value of the discriminant, absolute value of d, and then see how many of them are there as I go along of each class number. Okay? So in Dedekind domains such as these, UFD and PID are the same concept. So UFD is, or the ring of integers will be a UFD even only if it is a principal ideal domain. So how many of these rings are actually principal ideal domains? Okay. How do we measure that? We measure that using the class group. So we take, the class group is precisely measuring how far are we from all our ideals being principal. So it gives you a measure of like how complicated your factorization is in this ring. So we want to relate ideals, and two ideals will be related if they're in the same class in the class group, if and only if there is some non-zero alpha such that I equals alpha times j. Okay, so one fact is that any ideal in, for instance, z adjoint the square root of d, you can actually write it in this form. I'm going to use this form just because it's easier to relate it later to the quadratic forms. You can actually write every ideal generated as generated by over the z over the integers by two elements, a, an integer, and b plus the square root of d, everything multiplied by a fixed element s. Okay, so so this part here, so that part is this much, and then the ideal would just be all of them now, just multiply everything again by a number s, and you would get any possible ideal. And notice that in this shape, b and d and a are related in that it has to be put in a way such that b squared minus d is divisible by a. Okay, so you can write any ideal in that form. So what is the relation with quadratic forms? Well, it comes from, again, if you think of x squared plus y squared as your sort of like canonical quadratic form, x squared plus y squared are the norms of elements in z adjoin I. So where are the quadratic forms? We're going to take norms of an element of this ideal here, or this part of the ideal, take norms of elements in there. What are the norms? Well, the norms down to q, you multiply that number by its conjugate, and then when you do the algebra, you see that, okay, remember that this quantity was divisible by a, so, and it's actually divisible by 4a, so there's some integer c that will give you that b squared minus d is 4ac, and then you can write that c in here, and then you get that the norms are a times a quadratic form in x and y. Okay, so that's where the quadratic form appears. If you want to get exactly the form with a, b, and c, then you can do, okay, what about norms of elements of the form ax plus b plus the square root of d over 2? Take the norm of that, and then you get that the norm of those elements is a times a quadratic form. Okay, so we're going to try to exploit what we know about quadratic forms now to figure something out about the arithmetic of quadratic fields. All right, so for instance, when d is minus 20, the values of the quadratic form x squared plus 5y squared are norms of elements in the ideal generated by 1 and the square root of minus 20 divided by 2, which is the ideal generated by 1 and square root of minus 5, which is all the ring of integers. Yeah. So, and then when you have d is minus 20, with minus 20, you have that other form. And what's that other form? That other form would give you norms, well, the half of norms of the elements in this other ideal. So if you take an ideal in here and you take the norm, then you get those values of that quadratic form are related to those norms. And this ideal in particular is a prime ideal above 2. All right, so let me just check. Is this ideal above 2 principal? Is it principal, meaning is it in the class group? Is it equivalent to the ring of integers? Well, if it is equivalent to the ring of integers, then there is some alpha such that P2, this ideal, is alpha times O. And then what that means is also I can just write any element of the ideal above 2. I can write it as alpha times an element in my ring of integers. So I can write that equality and then take norms. And then I'll have the norm is multiplicative. So I have the norm of tau is the norm of alpha times the norm of gamma. If tau is alpha times gamma. And on the other hand, I can also take norms of ideals. The norm of the ideal above 2 will be the norm of alpha times the norm of the ring of integers, which is 1. So that gives me that the norm of alpha must be 2. So put it in the equation above about the norms, and that gives me that the norms in norms coming from elements in P2 will be twice a value of the quadratic form G, and on the other hand, will be 2 times a value of the quadratic form F. But remember that those two quadratic forms are not equivalent. So they, for example, they represent different primes. So if you cancel the 2s, now it's telling me that if P2 was a principal ideal, then these two forms would represent exactly the same numbers as norms of elements of different ideals. And that's impossible because, well, we saw the primes that are represented, the prime 5, the prime 2, appear in different forms, but they don't appear in both. So that's impossible. So this tells me that this ideal is not principal, and what I've done is use what I know about quadratic forms. Okay? So I'm going to stop here, and next time what we will do is use this to go the other way around. Okay, if now I have an ideal, can I figure out is it principal or is it not principal? And here I prove that it's not principal, but I'm going to be able to compare it and find, okay, now if I have a class group and I have a bunch of classes, in what class is my ideal? This is actually that if you've tried to do it manually without knowing about quadratic forms, it's actually quite complicated to figure out, okay, now is this ideal principal? And you have to figure out, is there something like, sort of like that? But knowing that these two forms represent different primes is actually saving us a lot of the more difficult part of figuring out if an ideal is principal or not. So we'll use what Gauss did, the reduction of forms, to figure out when ideals are principal or what class are they in. So I'll stop here. Thank you.